Okay. So up to this point, we are starting to look at the bending of uh, basically the beams or any members, and we look at how, for example, the stress would be changing to that, how the strength will change that, how we can do the calculation for that material. The next part is that what if the beam we are looking at, or the member we are looking at, is made of 2 or 3 or 4 different type of materials? So what if it's not all steel? The main example for that is for example, have you seen the concrete building? The concrete building is part concrete, part steel. Because you have the steel bar inside the concrete. So if you cut the cross section, part of the cross section is concrete, and the part of it is steel. So it's not made of a single material. So how we do it with a single material. Right now we're gonna a very simple case of what if it's made of 2 materials, and look at how we can analyze that. Later on, when you if you get to the specific design course, there is a standard and codes that walk you through exactly how to do the design. But here we'll learn the concept of that rather than the procedure of the design. So bending in composite material. So assume I have a beam that made of 2 materials. Assume, for example, steel and aluminum. That, and then there has a top part of that. So I have something like this, and it's going to be steel the bottom. So the bottom part is steel. E2 with modular of elasticity. I just call it E2 to make it general, but that's it's a steel and it has a modular elasticity. E2, and the top part is a aluminum. It has a modular elasticity of E1. And then I will bending it like this. So if I'm bending it like that, we know that the very bottom part of that, which is the steel, is going to be in tension, correct? Because it's move up. Very top part of the aluminum would be in compression. What if somewhere in between? What happened from here to here? So if I want to draw that, I will go and say, there are 2 things that I will draw. So I'm going to draw the cross section here. I'm going to make it the cross section bigger so I can see it. So assume I have the aluminum part. And then I have the steel. That's only it looks like this. So again, this part is steel, E2. If I go ahead and say the centroid for this shape, assume the centroid is going to be somewhere here. Assume this is the centroid. Before I started, just we know that if it's made of single material, the neutral axis where the strain is going to be zero, where the tension is going to be zero, pass through the centroid. Do you think it's going to pass through the centroid here?
No.
It does not. Why? Because I know that the steel is going to take much more of the loading than aluminum. So it's not going to be in the centroid anyway. So it should be somehow shifted in a way that the steel do its job. So definitely it's not going to pass through the centroid. So if I go ahead and say, okay, look. I'm going to have I'm going to just line there. It's the interface. And if I know the centroid is going to be somewhere there, assume the neutral axis is going to be some, I don't know where it's going to be, but I assume it's going to be there. The neutral axis. Then I'll go ahead and have the axis, two axes here. So I'm going to draw the epsilon and the sigma. Going to be the y. That's going to be the y. So for the strain steel is gonna change linearly from the top to bottom. It doesn't matter when it's gonna, when I bend it, steel is gonna be linearly compressed here, stretch here, and linearly from the compressed to the tension is gonna change. Where is gonna be zero? At the neutral axis, where it's there. So I know it's gonna be zero there, and then it's gonna be a stretch at the very top. Sorry, going up. So it's compressed at the very top and a stretch at the very bottom. Correct? So if it's compressed at the top, it's going to be negative or positive?
Negative.
It's compressed at the top, so it's going to be negative. So it's going to be at the very top, positive at the bottom. So goes from here to here, positive, and then goes to 0 at the neutral axis, and then go back to negative here. So that's going to be our epsilon. That's how our epsilon is going to change. So that's our corner. So positive in the bottom and negative in the top, because our shape is going to be look like this eventually. Not just our shape is going to be look like that. If I have an M like that, so it's going to be the epsilon here is going to be positive, the epsilon here is going to be negative. The same for the tension. So the sigma here is going to be positive, and sigma here is going to be negative. Now, you said here that the epsilon, the strain, change linearly. What about the tension? What about the stress? Sorry.
Change dependent on their elasticity?
Yeah, so the one that has the largest elasticity is gonna bear the larger load. So the is not gonna be changing linearly like that. So here, when I'm gonna draw it for the steel, so the bottom part is the steel is gonna be positive, correct? And it's going to be larger, I know that. So it's going to be positive. So it goes, for example, here. And then linearly, it goes to the interface. It goes, the interface goes there. So here it becomes negative. So it's positive here. So below the neutral axis is going to be positive, above the neutral axis it becomes negative. For the aluminum, it's going to be the different thing, because it's going to have the different, it's going to be a smaller. So at the very same point here, if the steel is that much, the aluminum is going to, for example, be, I don't know, half of it, for example. Because the aluminum can bear less force. If the deformation is the same, if the deformation is that much, the steel, the stress in the steel is going to be much more than the aluminum. So let's assume it's a start from somewhere here and then linearly increase. To here. And the entire tension in the aluminum is negative, because it's the aluminum part is above the neutral axis. So entire tension there would be negative. It's compressive. If I extend that line, that line eventually goes to 0 at the neutral axis. It's not extended, it will start from that point. See, it starts from here. But if I extended it, it should become 0 when it gets to the neutral axis. So, now what I'm going to do with that? So, before I go to 2 points, the first point is that the neutral axis does not pass through the centroid anymore. So, neutral axis does not pass through the centroid. So that's the first point. The centroid is there. The neutral axis is going to be below that or above that, depending on the material we have, but it's not going to be on that. The second part is that the strain still changes linearly. There's a break in the stress, but there's no break in the strain. The strain would behave the same as it was before. So the only thing that's going to change is the stress. So the strain changes linearly by distance from neutral axis. Same thing. Strain changes linearly by distance from neutral axis. So by the way, we know that here is in tension. Here is in compression. The same here. So same here. This part is in tension, and this part is in compression. So any question up to here? So up to here we didn't do anything, we just see what's happening inside the section. Now we want to see how we can actually analyze that. So to analyze this type of problem, the way that we can do that is that we have to replace one of the material with the other one. So we have to change the entire section to either aluminum or steel. So either we have to go there, hey, if I want to replace the aluminum with the steel, how much steel should I use there to behave the same? Or if I want to replace the steel with the aluminum, how much aluminum should I put there to behave the same? So here's the question. If I want to replace the aluminum with the steel, am I going to use more material or less material?
Less.
Definitely less, because the steel is stronger. The other way around, if I want to replace the steel with the aluminum, I should have much larger aluminum that can behave the same as the steel. So the section is not going to stay the same. So either depending on which one I'm converting to other one, it's going to become smaller or larger compared to what we have. So the next step is that go ahead and replace one of them with another. So in this case, I'm going to replace the I'm gonna replace steel with aluminum. So I'm just using, it's easier to see it what happened, so. Replace steel, which is gonna be the E2 with it's gonna be the E1. So my entire section is gonna be made of aluminum. So if I want to do that again, I'm gonna draw that section there. So if I have these, that's the steel. This is aluminum. I want to replace them. So I want the new section is gonna behave the same as the previous section. So if I want to replace it with the steel, the aluminum part would just stay the same. So the top part will stay the same. I'm gonna change the bottom part. I want to make it bigger. I'm gonna make it taller or wider or both. Because it cannot be this the same size. I need more aluminum. Correct? So if I want to put more aluminum, I'm gonna put it in the width or I'm gonna put it in the height or both ways.
You probably should do both, but you, in this case, do it lengthwise, like height.
So if I increase the height, what would happen here? My strain is not gonna be the same as before,
Yeah.
which I don't want that.
Okay.
I want to keep my strain exactly the way it was so I can see what I'm doing. So we never increase the height, because if I increase the height, we are gonna mess up with the strain. We only increase the width. So I want to increase the width. How much I'm gonna increase it? So I want to put the aluminum, lots of aluminum here, that I'm gonna make sure that it's gonna be this. So that's my new section. Now, how much should I put here that make sure these two behave exactly the same?
Compare their two elasticities and find the ratio between them and just to change it based off that.
Yep. So if I go ahead and say, that's correct, if I go ahead and say the ratio of these two, E2 divided by E1, I call it N. So if I go ahead and say, hey, N if I set the N is E2 divided by E1, then this distance, the new width in the section would become equal to N times B. So if this is B, if this section, if this width is B, this is going to become N. So the top part would still be the B. We don't change the top part. The centroid, the neutral axis that we says that we don't know where it's gonna be, and says, okay, assume the neutral axis pass here. That neutral axis passed through the centroid of the new cross section. So if the centroid of the new cross section is gonna be, okay, first draw it, so. This is going to be the neutral axis, so that's going to be the centroid for the new cross section. So it passed through the centroid of the new cross section. It doesn't pass through the centroid of old cross section. So if it's, for example, it's here, so it doesn't pass through that, but it does pass through the centroid of the new cross section. So that's going to be my neutral axis there. So now I need to, again, the strain stay the same, doesn't matter. But the tension, how I'm going to calculate the tension, the stress. The stress in the aluminum part doesn't change because the top part. The stress in the aluminum section is the same as before because I haven't messed with that. So if I want to write that, the sigma in the aluminum, which is negative, it's going to be negative NY ion. So sigma in negative MY divided by I. Y is distance from neutral axis in transform section, axis of transform section. So this is the distance from the neutral axis of the transform section. And the I is the same. I is the moment of inertia of transformed section. So both Y and I we calculated for the new section, not for the old one. Sigma in the still in the bottom part that was the still. So sigma in the part that we didn't mess with that was previous equation. Sigma in the part that we messed with that So look at here, the aluminum, we make it n times larger. So the tension in that is gonna be n time smaller. We made the cross section bigger, so the stress is gonna drop because the area increased. So I make the area n times bigger, so the stress is here in the transform section is n times smaller than what it actually is. You got it? I increase the cross section, so the stress is the force divided by area. I increase the area, so whatever I calculate here is n times smaller than what it was originally. You got that? So I have to, whatever I calculate here, if I go there and say, okay, it's gonna be my ion, whatever I calculated, I have to multiply it by n. So one more time, the tension in the transform part is gonna be n times smaller. So whatever tension I calculate here, I have to multiply it by n to get the original one. So it's gonna be n times my ion. So in the part that I didn't mess with, just the original equation that I have. The negative because it's in compression. It's going to be positive because of the tension. So the negative, positive depend on which way you are bending it. So the original equation is my ion. So the original section my ion, in the section that transformed is going to be n my ion. Multiplied by n. Question? In this case here, it's going to be E of steel to E of aluminum. What if I want to do it the other way? If I want to convert the aluminum to steel?
You just flip that fraction.
Here, you flip that fraction, and this time, instead of being larger than 1, it's going to become smaller than 1. So instead of widening the bottom part, if I want to keep the entire thing still, so it's going to be the same, and the top part is going to be narrower. We are going to very narrow steel on the top. So depend on how we are work with that, we might make it wider or we might make it narrower. Either way, narrowing it or widening it should be in the width, not in the height. So widening or widening. If the n is larger than 1. And narrowing or n smaller than 1 should be in the direction parallel to the neutral So we change the direction parallel to the neutral axis. Or basically we change the width. We don't change the height. That's all of it. Any question? So just remember, very quick, remember that if instead of I transforming the steel, I transform the aluminum, I change the aluminum to the steel and make it smaller, this end goes from here to there. Because the steel is not changed, the aluminum part this time changed, so you're gonna multiply the aluminum section. So whatever section you transform it, you multiply it by n. If I want to put it in there. This one is gonna be always like that, so. So, if y is in original section, then the sigma would be ny ion, positive or negative, depend on is it tension or compression. If y is in transformed section, then sigma, again, positive, negative, depending, it's gonna be n y. So any question about any part of that? so if we have a cross section, okay, made of steel and brass, so. So a cross section made of two materials. The steel in the center. Brass on the side. Steel is 29 times 10 to the 6 psi. And the moment is going to be 40 kips inch. And then we want the sigma max for steel and sigma max for the brass. So when you're dealing with this problem, these types of problem, usually it's easier to make it wider than make it narrower. Usually, either way, it's going to give you the same answer. But usually, it's easier to make it the entire section transform into the weaker material. So here we have the steel and brass. So the easier way to work with that is that I go and convert the entire section to brass, because brass is weaker than the steel. So if I want to convert that to brass, to replace it, I want to say, okay, I want to say this is equal to completely made of brass. So I'm going to have the left part. Then I'm going to have the middle part, which is going to be larger. And then I'm going to have the right section. So it's going to look like something like that. So I know that this part is going to be, so it's 0.4, it's 0.4. How much is going to be the center part? It's going to be n times the width, correct? So I need to calculate the n. So replace steel with brass. So I need to calculate the N. N is so remember that in this case, because I've used the weaker, so it should become larger. So it's going to be the E of the steel divided by E of brass. So it's going to be 29 times 10 to the 6 divided by 15 times 10 to the 6, which becomes 1.933. So here, this part is going to be 1.933 multiplied by 0.75. Would be equal to 1.45. So this is 1.45. So that's the new section that I'm gonna have. So then the new width here gonna be 0.4 plus 1.45 plus 0.4, which becomes, if I have them correctly, it should become 225. And the height is just the same as before. Now the centroid for this new section, because it is very specific because it's a rectangle. The rectangle is going to be the same right in the center, so that's going to be the neutral axis there. And then how much would be the C? C would be 1.5, correct? For both of them, because of the arrangement, in both of them is going to be 1.5. So now I can go ahead and say, hey, so calculate I. So I for transformed section. So I would be, it's a rectangle, so it's going to be how much? 1/12 of B H cube. So I would be 1/12 of the B is 2.25 times 3 cube. So I would be 5.063 inch. And then sigma max. So I'm going to first sigma max in the brass. How much is sigma max in the brass? It's the it's going to be in original section because we didn't mess with the brass part. So it's going to be MCIO. So sigma max, the brass would be M, which is how much the M? 40,000 times the C, which is 1.5, divided by I, which is Agree? For the steel, sigma max for the steel is gonna be MC iron, but multiply by M. So it's gonna be sigma max in the steel. It's gonna be 40,000 for the M, times 1.5 for the C, 5.063 for that, and the N is gonna be multiplied by 1.933. Question? So, if the arrangement of the material is like that, is gonna be, this is probably the simplest case that can happen. So, we're gonna be go the entire section. But if it's gonna be look like that, that each material will cover part of the height, usually it's more complicated. So let's look at another example. Next one, we're gonna have the steel and wood in the cross section, but they are not gonna cover the entire height. So I have a cross section look like this. There's a T-shaped steel beam that here has the wood attached to that, like this. So the wood section neither cover the entire width nor the height, just part of the section. So that's wood. Or timber. And that's steel. Dimension is just 75, 20, 75. The top is 200. Millimeter. All of them are in millimeter. And this is going to be 20 and 300. So it's 20 here, 300 here. For E for the wood. Is 5. Gigapascal, and E for the steel is 200 gigapascal. The moment that we have is 50,000 Newton meter. So the same as there, you want to know the sigma max for the steel and the sigma max for the wood. Oh, it doesn't want the sigma for the steel. The maximum stress in the wood and the stress in the steel. So sigma in the steel. Sigma is steel in top surface. So what's in top surface? So I want to know what's the maximum stress in the wood and what's the stress at the top surface of the steel. So we have to convert them one to another. So I have a steel, I have wood. Again, we can either convert the wood to a steel or a steel to wood. Usually I said that it's easier to go make the entire thing from the weaker material, so it's gonna wood. So it's easier to go and convert a steel to wood. So if I want to convert the steel to wood, what I'm gonna get is that I'm gonna get a very big shape. something like section. I'll have to make it. I'm gonna get something like that. The dimension might not be exactly accurate, but the shape is. These are the original wood, and this is the T-shape that it becomes large. Now, I want to transform it. So I want to replace steel with wood. So again, the N would be E of the steel divided by E of wood, which is going to be 200 divided by 12. Would be 16. So the dimension I'm gonna have, whatever I had before is gonna stay the same, so if this one is gonna be 0.075, so then in meter. So these are in millimeter. Let's convert them. The middle section would be the N times the width, which is going to be 16 times 20. So it's going to be 16 times 0.02, which would be 0.32 meter. The top part going to be 16 times again, 0.200, which would be 3.2 meter, and the height would not change. So the height would be 2, and it's gonna be 0.300. So I want to make these two equal. So now I have that cross section. I want to find the stress in that. What should I do the next? I have to find the centroid. Right? So the very next thing that I need to do is that I have to go ahead and say I'm gonna find the centroid in that. So if I go ahead and I consider x and y axis, I'm gonna make the x and y axis slightly different from the, so I'm gonna say that this is gonna be x. We know that it's gonna be somewhere on the y axis, so it's gonna be y. Okay. So to find the centroid, I have to break it into the shape. If I want to break into the shape, the easiest way that I can is that get the top rectangle and this bottom part as the second rectangle. This entire part, one rectangle, and the top part also as one rectangle. So if I want to find the centroid, so I know that the y bar, the x bar I know where it is, the y bar is sigma AI y tilde divided by AI. So I'm not gonna do the table thing, I'm just gonna write them. So for this section, for the let's start it with the, assume I'm gonna start it with the bottom one. How much is the y bar for the bottom one? From here, it's gonna be 150, correct? It's gonna sit some 150. But the y bar is 150 times the area. The area is gonna be can you add these three and give it to me? 0.75, 0.7, these three. bar is gonna be 300 and how much gonna be? 310, correct? So the 300 plus 10. And the area is gonna be 3.2 times 0.020. And it's gonna be divided by adding all the area together. 447 times 300 plus 3.2 times 0.020. Can you calculate that because I don't have it? You should call that 0.020. Why? Correct. Hold on. So the wire bar is sitting 200 millimeter above the, so it's gonna be the centroid is gonna be sitting somewhere. This is half of it, so it's gonna be sitting somewhere here. That's the centroid. That's the C. And so that's where my neutral axis is gonna be. That's the neutral axis. And then the bottom part I know is gonna be 200. What's the top part? 320 minus 200 is going to be 102. So what will be the next step?
Replace the wood with steel.
Say that again?
Moment of inertia. Oh, yeah.
Yeah, we have to find the moment of inertia for the transformed section, correct? So I have to go ahead and find the moment of inertia for the new section that I have. About the neutral axis. So remember that, right, probably there. You have to find centroid for the transform section. So that's the centroid of transform section. So when you're doing that, that's find centroid for transform section. Make sure that you remember that. And then you have to find moment of inertia for transformed section. So I want to find the moment of inertia. Moment of inertia about neutral axis. So now I want to find the moment of inertia for the these about the neutral axis. So I have to go ahead and say, hey, how much is the distance between each of the section I have? So I know the centroid for the bottom one is sitting at 150, correct? This rectangle. Let me redraw it very quickly. So I want to do it again. So that's what I have. If I it's just the same thing. So that's the X. That's the Y. And then the centroid. That's the Y. The centroid is 200 above that, so it's going to be the centroid, and that's the neutral axis. And then the centroid for the, if it's the section 1, it's going to be sitting right here, correct? That's the C1. And the centroid for the section 2 is going to be there, so it's the C2. So D1 is how much? If it's a 200 minus 150, it's going to 0.05. 50 and 2, so it's going to be at 210. 310. So 310 minus 200, it's going to be 110. D2 is 110. Can double check that I get them right. So those are the distances. Then the I is sigma I about the axis passing through centroid A d squared. So I would be, for the first one, is going to be 1/12 of the B, 7 times the height, which is 300 cube, plus the area, which is going to be 0.47 times 300, and D1 is 0.050 squared. So if I'm correct, so you said it's going to be 0.047, correct? And this is going to be 300, this is going to be 0.020, and the top is 3.2. Plus, so for the top part, for the number 2 is 112 times the B is 3.2 times the height, which is 0.020 cubed, plus the area, so you got 3.2 times 0.020 times the 0.110 to the power of 2. So if I have this right, the I should come up as 2.19 times 10 to negative 3. Do I have all the number? Then the next part is that to find the sigma. So I want the sigma max in wood. So sigma max in wood would be, how do I calculate sigma max in wood? So the sigma max in wood is going to be at the top or at the bottom? Going to be at the bottom, because this compared to neutral axis is going to be 200 here, it's going to be 120 there. So it's going to be, the 200 is going to be larger. So it's going to be sigma in the wood, max in the wood. MC divided by I. So sigma max in the wood would be M, which is how much M? 50,000 times the C, which is going to be 200, divided by I, which is going to be 2.19 times 10 to negative 3. So it's going to be positive or negative? So actually, you can say that the moment is how the moment is applied. So you're gonna just calculate it for the positive. now it wants to know that. So the same thing for the steel, the maximum tension, the maximum stress in the steel is gonna be in the bottom, but it doesn't ask for that. This is what's the sigma for the steel. So sigma steel in top surface. So I'm gonna calculate it like simple way, and then I will multiply it by n. So the sigma in the steel would be m c ion, and it's gonna be times n. And this time the c is the, so the sigma in the steel is gonna be how much the n? 16 multiplied by m, which would be, what was it, 50,000 multiplied by the c at the top, which is gonna be 1 point, and divided by 2, 19 times 10 to negative 3. So for the top, if I have all the right, it's gonna be how much you get for the wood?
I got 4.6 times 10 to the 4.6 megapascals.
Times the 6 years.
Yeah.
So it's gonna be 4.57 megapascal. That's gonna be 43.8 megapascal. If I have them correctly.